This lesson is about the theory of stationary stochastic processes, and it's going to help us advance in our journey towards modeling with ARIMA modeling. We're going to realize that showing theoretically that a stochastic process is stationary is going to require remembering how to work with expectations, variances, and covariance definitions that we learn in a probability class or in some advanced statistics class. We use those probability concepts learned in other classes to show how to calculate the theoretical expected value, variance, covariance, correlation function of two simple stochastic processes. We are going to show theoretically also what it means that a stochastic process is non-stationary. We are going to see only stochastic processes of order 1, such as the moving average of order 1 and the autoregressive model of order 1. But we are going to notice that they're very different in their autocorrelation structure. Whereas the moving average has significant autocorrelations at just lag 1, the autoregressive model of order 1 could have many significant autocorrelations. And that is going to require that we use the partial autocorrelation function if we want to detect that the process is an AR1 process. The low order models that we are giving you here as an example are used to make the theory easier to understand. We could have used more complicated models, but as you will see when we start doing the expectation calculations and so on, those will be much harder. So you will appreciate that we are only using simpler models. So why is it important that we see the theory of stationary stochastic processes? Well, because when we look at a time series, the time series is just a sample, a finite sample from the ensemble of all infinite possible time series that could represent the same model, the same stochastic process. So like all the summary statistics that we usually use, our ACF are full of noise. And that makes it much harder for us to understand the autocorrelation structure. It's very easy to interpret noise as something real when it is not. By looking at the mathematics of stationary stochastic processes, like we're going to do here, we're going to train our eyes to see the actual autocorrelations that should be there for a process without the sampling noise. That makes it easier for us to interpret the sample autocorrelation function of actual data. We are going to see actually the pictures of the theoretical autocorrelation functions using simulated data. So if the sample of the simulated data is short, there's going to be still some noise, but we'll show you how to get closer and closer to the theoretical functions. So consider this room time series. This is one of the typical series we have been looking at. It has a trend. It has a very regular seasonal that seems to increase over time. So obviously, there are deterministic features that are predictable and repetitive. Just by looking at the time plot, we can see them. There's an increasing trend, periodic seasonal effect. So those features do not let us see what's behind them. They're so prominent, they're so repetitive, so deterministic that maybe there is some other phenomenon or signal going on underneath that we cannot see if they still are there. So we need the theory of stationary stochastic processes. We have been trying to get to the random terms for a reason, because the random term is what you see underneath those deterministic components. And we want to understand it, we want to model it. So ARIMA models actually consist of fitting stationary stochastic models to the random terms of one observed time series, the one that we observed from the ensemble, and incorporating everything that we learn about the difference in the transformation in order to do the forecasting. So think about this ensemble that we introduced in an earlier lesson. The ensemble really represents the stochastic process. The stochastic process could manifest itself in many different ways. Any of these pictures could be a coming from the same model. Usually they will be fluctuating about a constant mean, and they will have some kind of vary according to certain variability. And then they will have a very common autocorrelation structure. But we don't see the ensemble, we only see one time series. You will see later on as we start modeling that there's a complex algebra involved in ARIMA forecasting, taking into account all these trends and the model for the stationary stochastic part and the seasonal and the pre-transformation. It's going to require some algebra. Okay, so in this lesson, we're just going to start by learning about the modeling of the random term using stationary stochastic processes. So we want to become familiar with these processes. So let's define theoretically what is a stationary stochastic process. And that should not be a plural there. It should be a stationary stochastic process without this SES at the end. I apologize for that typo. So a Y sub T, a process, a stationary stochastic process, is a weakly stationary stochastic process if the mean is constant. That means all those time series in the ensemble are fluctuating around a constant mean over time. And the variance is also constant over time. Now you will understand why we wanted to pre-transform to make the variance constant. And then the covariance between a time series and its lag version, lag K, and therefore its autocorrelation only depend on K. Okay, all autocorrelations and covariances depend only on K and not on time, on the time index. They do not change over time. In other words, if I have Y1 time correlated with YT with YT minus 4, should be the same correlation as YT minus 1, YT correlated with YT minus 5, because the K is the same. So in order to show whether a stochastic process is stationary, we need to remember how to use expectations, because we need to calculate that expectation, that variance, and show that they satisfy these properties: constant mean, constant variance, covariance that only depends on the lag K. Okay, so we need to use expectation operator, definitions of variance and covariance, learning probability classes. So what are those concepts? Well, here is a summary that I give in my probability class. If we have a discrete random variable, and when you are thinking about theory, the variable that represents the time series is a random variable that changes over time. Then if you have if your random variable was a constant, the expected value of a constant is a constant and the variance is 0. That's good to know. Okay, if we have a function of the random variable, the expectation of a linear function of the random variable is a linear function of the expectation. The variance of a linear function of the random variable is the constant squared times the variance. And if we have a linear function of the random variable, then the expectation is of the linear function is the linear function of expectations, and the variance is the constant squared times the variance. Then we have more, when we have more random variables, then we know that the expectation of a linear function of the sum is just a linear function of the expectations of the variables. And then if you have a variance of a linear function of the variables, then you have this other more complex formula: a squared variance x plus b squared variance y plus 2ab covariance xy. And then we remember ourselves that the covariance can be written as E of x minus EX is, well, that's the definition actually, but that's equal to also this other expression. Although I do not recommend using it in the exercises to show that a process is stationary, it can get confusing. So let's look first at one example of a stationary stochastic process, which is an MA1 process. So this is something that you're going to find in all textbooks. So consider your time series follows the following model: a white noise, right? The epsilon sub t, which we will call W sub t when we start modeling ourselves, plus a parameter, constant parameter, times the white noise at times t minus 1. We have talked about this model a little earlier. So the coefficient has to be between 0 and 1. And the epsilons of t are just white noise, right? So they have expected value 0. The variance is constant. So the noise is stationary. Remember, white noise is just stationary. So the covariance is just 0. Independent, so the epsilons of t's are independent, identically distributed random variables. And that's true for all logs k. So this is just basically your typical white noise, non-correlated, expected value 0 and constant, variance sigma squared and constant, and so on. So if you take the expected value of this model, right, the expectation of the y sub t, then you're going to be taking the expectation of a linear function of the random variables that are white noise of the epsilon. Remember the formula we just saw as review of a probability class. The expectation of a linear function of the expectation. So this term will be expected value of epsilon sub t, which we say is 0, plus theta times expected value of epsilon t minus 1. Since expected value is 0 for any epsilon sub t, that's going to be true for epsilon sub t minus 1. So the expectation is 0. Now let's think about the variance. The variance of a random variable is the expectation of the deviations of the variable from the expected value square. So what you do when you have a formula like this is you plug in the formula for the model. Y sub t is epsilon t plus theta epsilon t minus 1. So you just plug it in, and then minus mu. Mu we figure out was 0. So that's why it's important to start with expectation. So then you bring the expectation operator. Actually, you first I recommend, actually you already have a 0 here. So this is just going to be the expectation of epsilon t plus theta epsilon t minus 1 squared. So you know how to do that, right? A squared plus b squared, a plus b squared is a squared plus b squared plus 2ab. So you do that here for these terms and use the expectation of a linear function as a linear function of the expectation. There should be a parenthesis here right after e epsilon squared t minus 1 plus 2, right? Theta epsilon expectation of epsilon t times e epsilon t minus 1. Since expected value of epsilon t is 0, and so is expected value of epsilon t minus 1, this means that this expression here, e expectation epsilon t minus 1, is the covariance, right? Definition for the epsilon. And since we said as 0 for all k, right? Then this term is 0. So we are left with the variance, expected value of epsilon t squared, which is the variance of the epsilon t because the mean is 0, plus theta squared, the expected value of the epsilon g minus 1 squared, which is also the variance because for all t, the variance is constant sigma squared. So that reduces to this final expression for the variance. So we can see that does not depend on time. These are all constants. The variance is constant, the coefficient is constant, the mean is also constant. So we say this process is stationary in the mean, is stationary in the variance, but we need to show that the covariance depends only on the log k, or is constant, but it does not depend on time. So in order to do that, we have to use the expression for covariance of a random variable in order to calculate this, So I apologize for lack of parentheses here. There should be a bracket at the end of this expression. So we are going to calculate expectation of yt minus mu times yt minus 1 minus mu. So that's the covariance between yt and yt minus 1. And what you do is, again, every time you have yt, you have to substitute the yt by the model. So you put the model where you have yt. We found that the mean is 0, plug it in, and then start solving by using the properties of the expectation operator. You do the multiplication of these terms, bring the expectation operator inside, and use the linear property of expectations. And then substitute for things you recognize. Again, expectation of epsilon t minus 1, epsilon t minus 2 is going to be 0 because these epsilon terms are not correlated. The expectation of epsilon t minus 1 squared is just the variance because the expected value of epsilon is 0. So you're left just with a covariance for log 1 equal to theta sigma squared. And that is interesting, it's constant. Now, what about the covariance at log 2? Okay, here is an MA process of order 1, and it's ACF. Of course, it's simulated, and I only simulated 100 observations, so there is some noise that I was mentioning earlier that shouldn't be there, because as we will see, there is only covariance, that we found a covariance of theta sigma squared at log 1, but when you go to log 2, doing the same operation, you will find that the covariance is 0. So after log k equals 1, the covariance is going to be 0. So an MA process only has a significant covariance at log 1. Every other covariance is 0 in theory. Okay, in theory. So you will not be surprised then that an MA process only has a significant autocorrelation at log 1. Of course, with a small amount of data, you might also have that additional noise that shows up when you are looking at finite data. Therefore, the correlation, remember, is the covariance divided by the variance. That gives us correlation at log 0 equal 1, correlation at log 1 equal the value that we found. Okay, so it will be the theta sigma squared divided by the variance, which is 1 plus theta squared sigma squared. So the sigma squared disappears. Okay, and the rest are going to be 0. So because the expected value and the variance of an MA1 are constants and the ACF does not depend on T, the MA process is stationary. Now, for example, if suppose the MA process is YT equals 0.5 epsilon T minus 1 plus epsilon sub T. Here in the simulation, I use WT to represent the epsilon sub T. It's the same term. It's also a white noise, okay? It's the notation we'll use from now on in the modeling part in future lessons. So we find that the correlation at log 1 is 0.4. So you will not be surprised to find that the autocorrelation in the data is close to 0.4. If we had simulated more values like 1,000 or 10,000, that would be exactly 0.4 and there will be no noise. So since all the autocorrelations are 0, how come we don't see all of these values here, all these autocorrelations 0? Well, because of what I was saying. This is finite data, simulated. A finite sample is gonna show noise. Stuff that shouldn't be there, okay? This process, this MA process only has one significant autocorrelation, and that is 0.4. That's the only thing we should see. All the others are non-significant, but they're there. There's little things going on around, right? And they're distracting. So how can we view theoretical ACF and PACF on an MA process cleanly so that it looks like the theory that we got mathematically? Well, we can simulate a lot of observations to get close to the theoretical ACF and PACF. And here I simulated, I think it's 10,000 in MA processes of order 1, but with different coefficients. Of course, when you have so much data, you cannot see anything in a time plot. So it looks like this really dark band here. So in order to really know what's going on, you just need the ACF. Notice how the ACF has one significant autocorrelation, okay? And the PACF has a kind of decaying pattern. But all the ACF, even when you change the coefficient to become bigger from minus 0.3 to minus 0.9, you can see that it's always the case that is only one significant autocorrelation. That's always true from an MA1. Even if you have a short amount of data, you will not see it so clearly. You will have the noise in the other lags but if there is a clear MA signal, it's going to show this way. It's going to show with a significant autocorrelation at lag 1 if it's an MA1, and a decaying kind of pattern, a dying down or dying away partial autocorrelations as the lag increases. That's typical. And that can be seen if you have a lot of data, okay? If you don't have a lot of data, you have a finite sample like here, we only have 100. You see that, you'll see the a little r autocorrelation coefficient, sample autocorrelation coefficient, significant lag 1, but you're also gonna see the noise that's gonna distract you, okay? And remember, when we have a sample, we always have 5% that are gonna be significant other than the real ones. But theoretically, from the point of view of the expectations and operations that we did, there should be just one for an MA1 process, only one significant autocorrelation, okay? So that's why the PACFs become very helpful, because when you see a pattern like this, and then you see a pattern, that decaying pattern in the partial autocorrelation, then you can be more sure that you have an MA process. So I'm going to stop this here. And I'm going to split the video in two parts. And in the second part, I will give a separate video that will contain the discussion on the AR process, just to make this a little shorter.